So, okay, so we're recording now. So we'll start off. These slides were made by Christina Frayne. She's an F1 in primary care and public health. I'll put her email in the chat if anyone wants to ask any questions about her slides in particular, if you want to ask her. But basically, today we're going to just do a whistle-stop tour of basic statistics. So the expectations at interview aren't that you need to know every single statistical test, but to demonstrate that you have an understanding of the statistics used most commonly in studies. You only have 10 minutes, so it's not really about the quantity of what you say and like rolling off the names of lots of types of stats, but it's more about the understanding and the quality of what you say. Move to the next slide. So this is what we'll go through. We'll go through a few things like constructing a hypothesis, types of data, statistical models, understanding test statistics, interpreting forest plots, and we can talk through an example. There's also some slides on study types that I will try to run through quickly, but this is a kind of topic where a lot of your good points that you come up with for your interviews will be kind of like a self-study kind of thing. And through learning what statistics mean when you read every abstract. So it's like about making those cumulative gains when you read a lot of abstracts. So if we firstly talk about how you interpret the evidence, you firstly need to have a hypothesis that defines the purpose of the study. So the question would be, what are we testing? So in terms of the types of hypothesis there's a null hypothesis, and you'll remember this, I'm sure, from science in school. That's when there is no statistically significant difference between population observations. An alternative hypothesis is that there is a difference between the populations. So we call null hypothesis H0, and the alternative hypothesis is H1. H1 being the opposite of the null. The next thing we're going to talk about are variable types. So when you have data, we can split it into categorical/qualitative and numerical or quantitative. Categorical can be split into nominal, and that means unordered categories. So you can't order things like gender, male and female, or types of eye color. Another type of data is called ordinal, and that is when you can order things according to size or severity, and that's a scale, but it doesn't mean that you can quantify a number. So pain rated as mild, moderate, severe, or small, medium, large, those would be examples of ordinal. There's a clear order, but you can't assign a number to it. Whereas numerical can be split into discrete and continuous, and discrete are whole numbers, so that will be things like 1, 2, 3, 4, and then continuous is when in between any number you can have any value within a range. So that should all be familiar to you. Now if we talk about statistical models, there's a few different types. There's parametric or normally distributed data, and that is when data is skewed around a mean, and the data can be skewed towards a positive skew or a negatively skewed data. So in a positively skewed data, the mode and the median are less than the mean. That means more people fit towards the left of the mean. Whereas negatively skewed data, the mode and median is greater than the mean. And you can have parametric statistics that are based on data being normally distributed in this way. And we'll go through some parametric and non-parametric tests. So I mentioned that an assumption of a parametric test is that it's around a normal distribution, basically symmetrical. Another thing is that the data is homogeneous in that the data from multiple groups, they vary the same amount. And linearity, which is that the data have a linear relationship. Independence, it means that the data are not related to each other, they're independent from each other. And here are some examples of parametric and non-parametric tests. So parametric is paired t-test, unpaired t-test, Pearson, and one-way analysis of variance. And then here are your non-parametric tests. Wilcoxon rank, Mann-Whitney, Spearman, Proskauer-Wallace, and chi-squared. I wouldn't worry about this too much. It's not often that you have to talk about this, and most data actually tends to be normally distributed, and you want to think about doing a t-test when you want to see if two means are different. You want to do a correlation when you want to see if two numerical variables follow a trend together. And then an one-way analysis of variance, also called an ANOVA, is more for when you're looking at a categorical variable and its relation to a numerical value. So like rates of an MI in two categorical variables, so like male versus female. That would be an ANOVA. And you can do it with more than one categorical variable. So this is summarizing what I've just said. So you can see that if the data is normally distributed, you've got all these tests on the left that you can do. The middle tests are the ones if it's not normally distributed. And sometimes that is the case. And then the right column is going to be for when you would use that type of analysis. It's best, I know this can be quite overwhelming to think about, but it's best to just notice these terms and abstracts that you read and then go away and try and contextualize that in the study that you've read. So if you were asked to define what that test is, then you just learn this definition. It's something easy to make flashcards about. So in the next set of statistics, we're going to revisit some important definitions. I don't know if anyone's seen this. It's called the epidemiologist's bathtub, and it's quite helpful to understand definitions of incidence and prevalence. So firstly, incidence, that's the number of new cases in a specific time period. And point prevalence instead is the total number of cases at a specific point in time. There's something else called period prevalence, which is the total number of cases over a specific period of time. Yeah. So basically, with prevalence, that depends on the number recovered and the mortality. So the next thing to talk about is odds and risk ratio. So odds ratio is looking at the odds in a treatment group versus an odds in a control group. And this is used mostly in case control studies. This is where you often don't know the prevalence of a condition, and therefore that's why it's used in case control. Risk, however, is like the risk in a treatment group, which would be, if we look at this table, it would be the group A, so the event in the treatment group, over A plus B. You can't use something like relative risk in case controls because groups are defined by the outcome and the researcher sets the prevalence, i.e. you don't know the prevalence and therefore you can't do risk. And in RCT, conversely, you should know the prevalence because you should know your total population. So if they're using odds ratio instead, it makes you think that maybe their odds ratio looked a bit better, and therefore they're trying to misrepresent their data a little bit. Next thing is to talk about is a relative risk reduction. And the percent reduction is a percent decrease in the risk in the treated group, which is Y, compared to the control group, which is X. So there's just a formula for this, and that's basically the risk in the control group, X, minus risk in treated, Y, X minus Y, over X, so the control one. It's written in this table too. And this is an important one because it's similar to absolute risk reduction, which is risk in control minus risk in treated. And that is how we calculate number needed to treat, which is just 1 over absolute risk reduction. Yeah. So I'll just check the chat now, just if there's any questions so far. I know we're going fairly fast. Okay, there's nothing yet, but you can always unmute or just raise your hand if there is a question. So the next thing to talk about is sensitivity and specificity. So sensitivity and specificity is really important for interpretation of how good a test is. And here are some definitions. So specificity is about a proportion of patients without the disease who have a negative test or a true negative. And sensitivity is a proportion of people with the disease who have a positive test. There's a few other terms here, but sensitivity and specificity are the most commonly talked about. Other things that you might have heard are negative predictive value, NPV, which is the proportion of people with a negative test who do not have the disease, whereas positive predictive value is the proportion of people with a positive test who do have the disease. One talk I went to said that the most important one really out of this, or most useful one out of these, is probably negative predictive value. So that if people are negative, you can be sure that they are negative. Whereas if the other ones are off, you can usually interpret them in combination with other tests. There's a few other terms, so positive likelihood ratio, and that's how much more likely a positive test is to be found in a person with the disease compared to a positive test in someone without the disease. And negative likelihood ratio is the inverse. You won't really have to talk about those two so much, but I would be aware of sensitivity, specificity, NPV, and PPV. And you can see the letters in brackets are how each is calculated, and it's useful to just sit down and think about how that makes sense, because it can help your understanding. So let's continue on, talk about error. The types of error that we're going to talk about are type 1 error and type 2 error. So type 1 error is when you reject the null hypothesis when it's true. So basically you're saying that there is an effect when there isn't, and that's a false positive. So when you falsely reject the null hypothesis, that's a type 1 error, and the risk of this will be your p-value. So if you set a appropriate p-value, this type 1 error risk is reduced. Type 2 error is about not rejecting the null hypothesis when it is indeed false. So you say there's no difference when actually there is, and that's a false negative. So you're falsely accepting the null hypothesis. And the risk of this is 1 minus the power. It's also called beta. The risk of a type 2 error, I actually talked about this a lot of the times when I was appraising, because you can link it to sample size quite nicely, because the risk of a type 2 error is reduced with either greater observed effect or greater sample size. You can't really control observed effect because you don't know how big the effect might be sometimes for an intervention, but you can control the sample size. So when a sample is really large, you can usually assume that it's well powered, and therefore the risk of a type 2 error is reduced, and therefore you're likely to detect a difference if there truly is one. So for power, conventionally it's 80% that's acceptable, and it's the probability that a type 2 error will not be made in the study. Already mentioned that you can increase it by increasing sample size or increasing expected effect. Another few ways are increasing precision of measurement and also increasing the follow-up time. So how else can we test the hypothesis? You can talk about a few different things. The p-value, which is the probability that an observation has occurred by chance, and then confidence intervals, which is how sure are you that the result is close to the real result. A confidence interval is good when it's narrow, and that means it's more likely to represent a true effect, and a large confidence interval is less likely to be significant. You can also talk about something called regression, which is an equation that allows you to predict one variable from another, and we'll talk about this in a bit more in a second. And correlation. So that's the strength of a relationship denoted by R values. You might remember this from A-level biology when we had to do like Pearson's rank and stuff, and you get an R. If it's close to 1, that's a very strong, perfect correlation. 0 is no correlation. And then causation. So neither correlation nor regression shows causation. Causality must meet something called the Bradford-Hill criteria. I don't think we have time to go into that, but you might want to look that up, and it's about key features that are needed to be observed to say that something causes something. And it's about things like whether it's reversible, whether the effect increases with larger intervention, whether it can be, there's a biological mechanism for explaining it, and there's 5 more other things, I think. So when it comes to p-values, the cutoff is 0.05, and that's a reasonable cutoff to reject the null hypothesis. Here are a few different just examples. You can see as the p-value gets smaller, the more highly significant the data is. We already talked about type 1 error. That's also called an alpha. And there's something called the Bonferroni correction. So when you read a study and they've investigated many, many outcomes, this can kind of be fishing for an outcome. And therefore, this significance level needs to be adjusted to account for that. And they should accept a tighter p-value. They should set a tighter p-value for a level of significance to offset investigating multiple outcomes. Okay, so if you do n tests, then for each test, only accept as significant tests with a p-value of less than 0.05 over n. So if you had 2 outcomes, that would be 0.025 instead. Okay. What about confidence intervals? So a 95% confidence interval gives you a range which you can be 95% sure the true value lies. And I already talked about the narrowness and the wideness of this range. But if a confidence interval crosses 1, then there is a 95% chance that the true value lies within a range that includes no difference. And therefore, you can't definitively say that there is a difference. So we'll talk about now relationship regression. So regression sounds complicated, but it's really about plotting a line. So when you have two numerical values, you can plot a line with y equals mx plus c, or b here, basically. So the beta, we'll talk about that in a second. So the p-value for the regression coefficient is a probability that the true gradient of the line is 0. And in a null hypothesis, the gradient is 0. The line is flat. There is no relationship. And you can use this when you've got two continuous variables that you are comparing. So basically, you're looking at the size of the beta for the strength of the relationship. Whereas a logistic regression, instead, is denoted by a C-shaped curve and uses something called the logarithmics of odds rather than probability. And this is usually reserved for binary outcomes because you can kind of see it's a step kind of appearance that's binary. So it's either there or it's not. Yeah, I wouldn't worry about this too much. Next thing to talk about is relationships between things using correlations. So strength can be measured by an R value, and I already mentioned that +1 would be a perfect positive correlation, -1 would be perfectly negative, 0 is no correlation. Oh, okay, Christina has included the Bradford Hill criteria that I mentioned earlier. Talked about strength, talked about biological plausibility, if there's a mechanism for it in the literature, and gradient, that's what I talk about. So coherence is about if there's multiple studies showing the same thing, it's more likely that there is a causal relationship. Consistency is if the effect keeps occurring, then there's more likely to be a relationship. There's experimental evidence as well, if it's specific for that one intervention as well, and if it's temporal, as in the outcome should occur after the exposure, then there is likely to be a cause or a link between the two. Next thing we're going to talk about is forest plots. So a forest plot is used often in meta-analyses where you're looking at multiple studies to see if they answer a specific question. You have a line of no effect that's 0 or 1, and that really depends on what's measured. And with a forest plot, you can see the skew towards the right is what correlates with a larger effect size, and the study weight is indicated by the size of the square, so how much that could be attributable to how large a sample size was, things like that. And then this diamond summarizes the pooled overall averaged effect of all the studies. So we've gone really fast with that. I'll give you, we can talk about this one in a few minutes. I'll give you a few minutes to think about it, and then if anyone can put up their hand or talk through it. Anyone want to have a go interpreting some statistics? Just highlight a few things. Alternatively, you can just type a sentence of critique in the chat. Large sample size is good power. That's right, exactly. So 4,300 is a pretty big study. You can also even say that to show that you know it exists as a thing, that you could say that I assume this study has been adequately powered as 4,000 participants is a large sample size, but I would like to see the power calculation to ensure that this is the case and that the risk of a type 2 error has been reduced. That's a lot of things that show that you kind of know a little bit of stats. I'll talk about the next thing that I highlighted. It's not really a statistic thing, but a follow-up period of 2.4 years is really long. So you can say that that would reduce the likelihood of a type 2 error as well, because it's a long enough time to detect a difference. And the next thing that I highlighted here was about the primary outcome event occurring in less people in the dapagliflozin group and more people in the placebo group. And it's basically showing that there is a 39% reduced risk because that hazard ratio is 0.61. So I did 1 minus 0.61 to get 39%. The 39% less likely to have a sustained decline in eGFR if you're on dapagliflozin in the context of CKD. And we can interpret the confidence interval by saying that confidence interval is less than 1, and it's also fairly narrow, ranging from 0.5 to 0.7. And this indicates to me that this difference is likely statistically significant, and this is also supported by the fact that the p-value is less than 0.001. All of the things that I've just said, though, you would have to be ready to define anything that you just said then. So like, what is a confidence interval? What is a p-value? What is a hazard ratio? So careful to know how to define anything that you mention. The other few bits that I highlighted were just the same type of thing that you can explain as well by saying that the hazard ratio for composite of sustained decline was 44% less in the dapagliflozin group. So that's when they combined all the outcomes together. And that's probably a more useful measure because we want to know overall risk of harm rather than just one risk of harm for one particular negative outcome. And they've given you a few other useful bits of data there about risk of death, which is very important, of course. And they've given you Yeah, they've given you the risk of death. So you can see they've also measured for a few different outcomes, but you can also mention here that while they've measured for a few different outcomes, their p-values are very small, and therefore the risk of the need for a Bonferroni correction, because they've measured multiple outcomes, is less applicable because their p-values are so small. Because remember, I said that if you test for multiple things, you need to reduce the p-value so that your threshold for detecting things is smaller, because you're essentially fishing for an outcome. So that's another strength of this abstract. Yeah. So Christina has nicely compiled a long list of things that you want to know how to define in the context of statistics. So I would definitely look at as many of these as you have time for each week. Just chip away at this list. And now I'm going to briefly talk about study designs. You may have already seen this, which is the hierarchy of evidence. Things that have been reviewed or an amalgamation of multiple studies, like systematic reviews, meta-analyses, sit at the very top. And then you have your single studies, which are RCTs, and those sit highest because they're interventional. Observational studies come next, and cohorts are better than case controls, but cohorts require many more sets of data. And case reports are because they're just a singular bit of information about one patient, often, unless it's a case series. At the bottom, and then at the very bottom, there's expert opinion, because that's prone to lots of types of biases. So in all types of studies, what we're trying to do is establish if there's a causal relationship between any kind of exposure and a kind of outcome. The exposure could be some kind of treatment or some kind of risk factor like a gene mutation or something like smoking. And the outcome could be a medical diagnosis or a serum level of an inflammatory marker like CRP. So if we start with exposures and we go forward, when we start with outcomes and we look back, so you compare a group with an outcome to a group without an outcome, and you look back in time to see what those exposures are, that's called a case control. So you start at the outcome. And you're going back to see what exposures do they have different. Case control has a few different pros and cons. So pros, it's cheap, fast, useful for long latency diseases. So when there's a long period between the time of the exposure and the development of the disease. It's good for rare diseases, and you can also assess for multiple exposures. But it does have significant limitations, and that's that it's retrospective. It's prone to something called selection bias because you've chosen cases and chosen matched controls. Prone to something called recall bias as well, because can the patient remember correctly what they were exposed to at the time? And it's hard to establish risk because the researcher has already set the prevalence rate by selecting based on outcome. You can't establish a true prevalence with a case control. So like I said, with the case control, we generate an odds ratio. But luckily for rare diseases, odds ratios will be very similar to relative risk. They can be approximated, basically. Next thing to talk about are prospective cohort studies. And this is where we start by defining our groups in terms of their exposure. And then we wait for time to elapse and we see if they develop different outcomes. So for this, it's good when we're trying to establish risk directly. We can assess for multiple different outcomes as well. And it's useful for rare exposures because you start with those rare exposures and you just follow them forward. However, it's obviously slow, expensive because of the time invested, and it's not good for rare diseases because those few that you've picked within exposure are unlikely to develop them, and is not good if long latency because you'll be waiting a long time. So if we talk about retrospective cohort now, so a retrospective cohort is similar in philosophy as a prospective cohort, except everything's already happened. So here, there's already exposures and outcomes that are measured somewhere, but we're just basically going back to a pre-existing data set that was collected, and we're starting with the exposures and seeing what those people develop, all from a retrospective standpoint. And we can take this data set to ask new questions in the form of a cohort study. The exposures are defined before we look at the existing outcome data to see whether their exposure to a risk factor is associated with the outcome. This is not the same as a case control study because we can establish risk, because in a large data set you can find out the prevalence. And now with an RCT, we start even further back in time, and here people haven't even been exposed to something yet. So we define two groups who should be identical because we randomize them to be that way, and then we manually introduce different exposures to the two groups, we manually introduce different exposures to the two groups to introduce a real causal manipulation by which we can test whether this exposure truly causes some variation in this outcome. This is the gold standard for testing causality, and it removes selection bias in theory, and if the methods are done correctly with proper randomization. But it's expensive and it's slow. And there are modifications to all of these different types of studies. For example, with randomized control trial, there are crossover trials, there are N of 1, and within each of these trials, there are also different types. And I would encourage you to just be aware of each even weird type of study, because in London interviews, I have heard of some of my colleagues getting abstracts that are a bit weird, like an N of 1 study. So be prepared for anything, but know your RCTs the best, and then know your observational studies, and know your reviews and your meta-analyses. This is a table just to summarize all of the strengths and limitations of these different types of studies that I've just kind of talked about too. And yeah, I can also, if people are interested, link some of the Quizlet decks that I used in addition to my Anki deck, just to kind of make sure I read and learn what this type of study meant and that type of study had in terms of limitations, because it's a lot of information otherwise. So here's Christina's list of references, and that is everything. So I appreciate I went quite fast, but can I take any questions? I'll just pause the recording.